Hello, my name is Rita and I'm here to talk about my master thesis. I know it's a long title, but let's start with some basic concepts on particle physics. As of today, we know that matter is made of atoms. These atoms are divided into electrons and then the nucleus with protons and neutrons. But it turns out that this is not all. The protons and neutrons are themselves composed of even smaller particles called quarks and gluons. These are just some of the fundamental building blocks of matter that are organized in one of the most successful theories built until today, the Standard Model. The Standard Model includes matter particles, the fermions, that are divided into quarks and leptons, and then the gauge bosons that mediate the fundamental interactions. Let's focus on the important ones for this study. We have the up and down quarks that make up protons and neutrons. We have the muons, which are the electrons' heavier cousins. We have the photon, that you probably already heard about, and then we have the gluons that mediate the strong force. The theory that describes the gluon-quarks interaction is called quantum chromodynamics, or QCD in short. According to this theory, besides the electric charge, the quarks also carry a color charge that defines their interactions. The theory also says that due to confinement, we cannot observe a quark or a gluon isolated. They are always organized in bound states called hadrons. Hadrons are divided into baryons and mesons. Baryons are, for example, protons and neutrons, while mesons are particles made of a quark and an antiquark, like pions or kaons. Now that we already know about the important particles, let's move on to the Drellian process. Drellian is a rare process where a quark and an antiquark annihilate, creating a virtual photon, which then decays into a pair of a lepton and antilepton. We will study a hadron-hadron collision between a charged pion and a nucleon, resulting into a pair of a muon and anti-muon. By analyzing the muon's properties, we can infer information about the hadrons that collided. Some experimental observations are not in agreement with the predictions. So, we need to upgrade our model. From the simple diagram with electromagnetism, we can also consider the QCD processes. So how will we study this? We will use the AMBER experiment. AMBER is a future fixed target experiment at the M2 beamline of SPS, the Super Proton Synchrotron at CERN. AMBER will follow the footsteps of the ongoing COMPASS experiment, performing a great variety of measures on fundamental issues in QCD. For the Drellian program, we will have beams of both charged pions at 190 GeV colliding with tungsten and carbon targets. The muons produced don't interact much with matter, and they will only be detected at the end of the experiment on the muon filters. For our analysis, we need to be able to reconstruct with accuracy the trajectory and properties of the muons. To do this, we want to add vertex detectors. These do not exist yet, so there is a need to explore and study several options, with different dimensions, materials, geometry, for example. And to do this, we need simulations. And that's where I come in. For the AMBER experiment, we have a full simulation chain where we can simulate the Drellian process, reproducing the detectors and simulating their answer. And with this, we are able to reconstruct the tracks and properties of the particles produced. In the end, we are able to analyze all the distributions. I am now implementing the vertex detectors on the simulation chain and studying how different features impact on the reconstruction of the Drellian kinematic distributions.